Okay, so we are starting with page 30, question 11, as a little starter of a reminder of the previous lesson. So we've got two events. Anna is late and Bella is late. Those aren't mutually exclusive, so there's an overlap there. I'm going to start off by filling in the information as it's given to me, but it may well be that I have to change it. The probability of not in A and not in B is there. But of course I've got a problem here, haven't I? I've got more than one. So, Jacob, what would the solution to my problem there be?
What is what going in the middle?
Yeah.
Point one as well.
So yeah, it must be that point one goes in the middle. If the total of those is point one too big, if I put a point one in the middle, which means that I have to knock that down by point one and knock that down by point one, so that's still 0.3, that's still 0.7, but what I now have is a total of 1. So I spotted that just by filling in the information without the overlap, I got 1.1, which told me that I had to add 0.1, but take away 0.1 and take away 0.1, which overall got me right. So the probability that Anna and Bella are both late to school, well, using notation, that's that one, so that's what we've just worked out. So this is the given that notation, isn't it? The probability that Anna is late, given that Bella is also late. So this is going to be, I'm always going to write this as a fraction. The probability that Bella is late gives me my denominator. Of that, what part of that is down to, is Anna also late in? So that's 1/7. The teacher suspects that Anna and Bella being late for school is linked in some way. So the teacher suspects that the two events are not independent. So let's test for independence. If they are independent, the overlap will be equal to the probability that one's late multiplied by the probability that another's late. That means that one is not affecting the other. The teacher is suspecting that actually one is affecting the other. They're, perhaps bumping into each other and slowing each other down. So let's just test. The probability of A is 0.3 and the probability of B is 0.7. That does not equal the probability of the overlap. So the events are not independent. So the teacher's suspicion could well be right. Well, they go even further. Because the overlap is less than we expect, if Anna is late, Bella is less likely to be late. Oh, that's interesting. So it's not... I'm trying to think how that could happen. But anyway, it's not that if one is late, the other is more likely to be late. It's if one is late, the other is less likely to be late.
Sure, if the events are not independent, and if Anna's late, Bella can't be more likely to be late.
But no, they're not independent. We've shown they're not independent.
Oh, okay.
Because 0.3, the probability of Anna being late, multiplied by 0.7, doesn't give us 0.1, so they're not independent. Okay, so today we are going to talk, and this is the final piece of new content. There's a tear in my eye as I write it. We're going to talk about conditional probability and tree diagrams. Actually, it's not quite the last bit because I've got a short list of things that we skipped along the way. Parametric integration, differentiation of trig by first principles, but that's all good, that's good revision. And this is, the good news is that to a large extent, the vast majority of these questions are GCSE. It's just there is nearly always a part C or a part B which just extends it slightly, and that often involves the use of a given that And surprise, surprise, here in this example, we see that key phrase, given that. So, I hope you can knock me up a tree diagram for this question. This is one of those questions where you've got different coloured balls in a bag, you take one out and you don't put it back in. So your first choice could either be green or yellow. So we tend to sort of put the name of the choice at the end of the branch and then the probabilities on the branch. And if you take a green out, you could still get a green or a yellow for the second one. And if you take a yellow out, you could still get a green or a yellow for the second one. But of course, by the time you've taken one out, there are no longer 10 beads in the bag. All right, so hopefully you can knock up that tree diagram.
Put the probability along the branches.
Yes, that's the way we tend to do it. I don't cancel my fractions because it just means that I end up with nice easy sums to do at the end. Final answers I'll cancel.
Why don't you cancel?
Well, it just means I'm dealing with fractions with a denominator of 90 at the end, so if I need to add...
Could you cancel?
Yeah. And in this case, you actually... it's not a huge problem. Now we could throw in some of the notation that we've used. So for example, this probability here is the probability that you get a yellow with your second bead, given that you got a green for the first bead. That's that probability, isn't it? And we could use that sort of notation throughout that diagram. I mean, well, I'm not going to, but that's the answer. So, if the question had said, given that the first ball is green, what's the probability that the second ball is yellow? The answer would be 4/9. Given that the second ball is yellow, what's the probability that the first ball, given that the first ball is yellow, what's the probability that the second ball is green? Well, that would be 6/9 or 2/3. So we've got some conditional probabilities here. However, if the question said, given that the second ball was green, what's the probability that the first ball was yellow? Or, given that both balls are the same colour, find the probability they're both yellow, those probabilities are not immediately obvious on our tree diagram. So I'm going to answer this question here, and then I'm going to answer my supplementary question, which was, given that the second ball is green, what's the probability that the first ball was yellow? So this one here, Given that both balls are the same colour, find the probability that they are both yellow. So what this is, let's use our given notation. This is the probability that they are both yellow, given that they are the same colour. And why have I bothered writing that sentence in that way? Because it reminds me about the whole numerator-denominator thing. So my denominator is going to be, what's the probability that the two balls have the same colour? And that's this added to this. 42 out of 90. Now, of that, so let's highlight the two. So this is the probability that they're both the same colour. Of that probability, which part of it is down to both yellow? Well, that's this one, isn't it? So this is, like in the Venn diagram, what's the probability you get the same colour? 42 out of 90. Of that, looking at that those probabilities only, which part of it involves both yellow? And hopefully you can see that that would cancel to 12 over 42, which would cancel to, is that 2 7? I think it is. Now, I also had a supplementary question. I said, if the second ball's green, what's the probability that the first ball was yellow? And our tree diagram is drawn the wrong way round for that. So let's work out that one. What's the probability that the first is yellow, given that the second is green? Now, why have I written it like that? Again, it helps me think about the whole numerator-denominator thing. So the probability that the second ball is green is going to be my denominator. And that's those two outcomes, isn't it? 30 out of 90 and 24 out of 90. Of those two, what part is down to the first one being yellow? Well, this is not. But this one is. So it's that part. What proportion of this involves this? That's what we're asking there. And again, that's going to simplify.
Or is it not 4 over 10? The first ball yellow.
No. So what we're saying is of the outcomes where the second ball is green, which of those involved the first ball being yellow? So it was that outcome there. So 24 out of 54. What's that? 12 out of. Now we could do this using that formula. Do you remember the formula? We said, right, the probability of B given A is the probability of A goes on the bottom and the probability of B intersection A goes on the top. So we could have sort of used the formula. That's all we're doing. That formula is the formal statement of what we're saying here. B given A. What's the probability of A? Probability of second green, 54. What's the probability of these two things happening together? The first one being yellow and the second one being green, 24 over 90. So I'm not a fan of using the formula. We did have that one question yesterday where it was probably necessary because it was a bit more sort of algebraic, but you know, this is just an application of that formula. So we are going to have a go at a few questions which practice this. The first of which is on page 31 and question 1. It actually continues over the page. Are we all booked up? So the second token is red, given that the first token is blue. That's given to us. The second token is red, given that the first is blue, is 5/8. It's not 20 over 72. All right? It's just we've given this, what's the probability the second one's red? So that's a straightforward question. Don't automatically assume these have to be super complicated. The tree diagram is the right way round for that question. Given that we're here, that's what it means, we're here. Given that the first token is blue, what's the probability the second token is red? It's just 5/8. So with that one, the tree diagram helps. And it's really important that you can spot those simple ones, because some are simple, although there are plenty of non-simple ones. So for example, part C our tree diagram doesn't help us because it's the wrong way round. So we want the probability that the first token is red, given that the second token is blue. So it helps me to write it in that form to remind me about my whole numerator denominator. Second token is blue, that's that and that. So that's 32 out of 72.
Which one are you doing now?
I'm doing part C.
First token is red, given the second token is...
So first red, given that the second is blue. So the second is blue, the probability of those two added together.
Yeah, no, even with the previous one, it's still the same thing, because you're doing 4/9 times 5/8 over 4/9, so the 4/9 cancel out.
Yes, I suppose you could do it that way. Yes.
Yeah.
So of those two, which involve the first one being red? Well, it's that one. So that's 20 out of 72 divided by 32 out of 72, which is 20 out of 32, which simplifies to something or other. And the first token is blue, given that the tokens are different colours. So again, my denominator is different colours. So different colours is that and that. So it's 40 out of 72. Probability the first one is blue. Which of those two involve the first one being blue? It's that one. So that's a half. 20 out of 40, which is a half. Do you see now why I don't cancel? Because it means I've got the same denominator, so that last step is nice and easy. But you've all got calculators, so it's not a problem. And lastly, the tokens are the same colour, given that the second token is red. So again, I've written it out in that form to help me. Second token is red, are those two. So that's 40 out of 72. And probability that they are the same, well, that's the 20, so that's a half again. Check that I've done that right.
Yeah, okay, alright, thank you.
Okay, so for those at home, I'm suggesting you try these 3 questions. I'm going to pause the video now and come back to do question 8, 6 and 7. If you have any problems, please come and see me. Okay, Lyle, I've actually got number 7. So the way I did the tree diagram for number 7 is I've got the 3 factories, A, B and C, turned my percentages into decimals, and then each factory might either produce sheets that are okay or flawed, okay or flawed, okay or flawed. So that's my completed tree diagram. So part B, no mention of the word given. So part B is straightforward, it's GCSE. So factory B and flawed is this outcome here, 0.45 times 0.07. Flawed is this one, and this one added together. So it's 0.25 times 0.02 plus the previous answer plus 0.3 times 0.04. But then part C is the given that question. So I've written it in this form to remind me about the whole numerator denominator thing. So the probability that it's flawed, well, we've just worked that out. That's the previous answer. Sorry, it's just gone again, isn't it? So that's 0.0485. And of those outcomes, which of them involved A being flawed? Well, that was 0.25 times 0.02, which was that. So that's the sum, which gives you 0.103 when rounded. So that's number 7. And so here's number 8. So you've either got the condition or you haven't, 4% chance of having it. And if you test with the condition, 90% chance it tests positive, and a tiny chance that you test positive if you haven't. So the probability you test negative, it's those two added together. So given that the test is negative, which we've just worked out, so that's the denominator, what's the probability that they do have the condition? So we're saying of those two probabilities, what proportion involves actually having the condition? So it's that branch there. So it's that part out of that. So what that comes out as is 0.00423. So that is the probability that they are negative, given that they do have the condition. So that is a false negative, which is okay. But what they'd actually then, so actually, Jacob, I didn't quite answer that correctly, did it? Because they are commenting on more than just part C. They're commenting on the chance of a false positive. So the chance of a false positive is 0.96 times 0.02. Probability over 1/3 of positive results are false positives, and 10 people with the condition give negative results. Yeah, I guess, although the chance of a false negative is very, very low, you are getting I don't like that answer anyway. Yeah. I think chance of a false negative, if you've got the disease, you want the test to test positive, so I think that's pretty good. Right, for those at home, I've recommended 3 questions from the mixed exercise. You've got a Venn diagram. I think that one I recall is you could do with a 2-way table. You don't have to, but 2-way tables was something we did. And then you've got a tree diagram. So I commend those 3 questions to you. And that is the end of probability. And that is the end of the syllabus. Wowzers.